On BBC Learning Zone now, a mathematical journey from a Victorian garden to a space telescope in Reflecting on Conics.
I was always told that the trouble with pure mathematics is that it has no applications. Hence, it's difficult to understand its role in the real world. Yet, pure mathematics underlies much of the world around us. All you need to know is where to look. This is the story of one small part of one area of pure mathematics and how I came to reflect on conics. It had all begun with a phone call from one of my maths tutors, David. He felt that I needed to experience my mathematics, to get in touch with how maths could serve me in the real world. So he called and invited me to lunch at the home of the Royal Horticultural Society in Wisley. So you were telling them. So I'm here at Wisley and it's really very lovely, but what am I here for, David?
Well, I wanted to tell you about conic sections. So, let's suppose that we start with a double cone like this. Say the cone has circular cross-section.
Okay.
Now, if I cut that double cone with a horizontal plane, the curve of intersection that I get is a circle.
Okay.
And if the plane is at an angle, the curve of intersection that I get is an ellipse. If the plane that I use is parallel to the generator of the cone, the curve of intersection is a parabola. And if the plane that I use to cut the cone is vertical, the curve of intersection consists of this double curve. That's called a hyperbola.
Well, that's all well and good, David, but what use do conic sections have in the real world?
Well, many and varied uses, Joan. Let's go to see.
All right.
Hello, Maggie. Nice to see you again.
And you.
The woman that David introduced was Maggie Whittaker, a senior instructor on the horticultural course at Wisley. During a brief tour of the gardens, Maggie told me about the course that she runs and how her students use mathematics when laying out formal gardens. One particular example is a flower bed in the shape of an ellipse. I knew that it was possible to draw an ellipse if you knew the position of the two foci. But what if you wanted it a particular size? Maggie and one of her students, Julie, offered to show me how the elliptical flower bed was pegged out. They began by marking out the two endpoints of the longer axis of the ellipse to a value of 2.5 meters. So what are you doing now, Maggie?
Well, we've just marked out the major axis. Now we're going to do the minor axis. We've got to make sure that it's at a right angle to the major axis.
Okay. The length of the shorter axis of the ellipse will simply alter the fatness of the shape. In this case, it was 1.5 meters.
Over to me a bit. So pull it out tight a bit more.
The trick that Maggie uses is to create a simple 3-4-5 right-angled triangle between the two axes.
Now we have worked out whereabouts the outer perimeter of the ellipse is going to be using Pythagoras' theorem to ensure that we have got right-angled bisection of the two axes.
Yeah. Having found the right-angled triangle, Maggie marks up the end points of the shorter axis. This gives the dimensions of her particular ellipse. So what's next?
Right, next we've got to find the two foci on the major axis for the ellipse, and that will give us the points from which we can work out where the perimeter of the ellipse is.
Finding the foci of the ellipse is the clever part of this procedure. So Julie's just creating a mark for you to spot like that.
That's right. We're just creating the first half of a pair of intersecting lines.
By taking a rope half the length of the major axis and placing it on the end points of the minor axis, Maggie could mark out each focus without using a tape measure. She then staked out each of the 2 points. So what's going to happen now?
Well, we're now going to use the piece of string which is equivalent to the major axis of the ellipse. And we're going to set that at the foci, which will give us a little bit of slack, which will enable us to draw out the perimeter of the ellipse, because obviously as one piece of string shortens here, it's going to lengthen there, and it's going to pull us in around in a like an arc.
Yeah. As Maggie began to mark out the ellipse, Julie used silver sand to highlight the shape.
Very neat, indeed.
Despite the fact that all Maggie's students learn how to mark out these flower beds, they're rarely seen in gardens today. Perfect. It looks like the perfect ellipse. All they needed now were the flowers. To find out more about the origins of this elliptical flower bed, Maggie suggested that I try the library. I was amazed to learn that it was the publisher husband of Cookery's Mrs. Beeton who formalised the use of elliptical flower beds. Apparently, they occurred frequently in the best-kept Victorian gardens. But where was I to go from here? Once again, it was David that provided me with my next lead.
Well, John, how did you get on?
Well, I can pick out a mean flower bed, but where does the mathematics fit in?
Well, what you need is the focus directrix definition of the ellipse. Let me show you. If you take a point, and we'll call that the focus of the ellipse, and a fixed line, we'll call that the directrix of the ellipse. And we take a typical point, P, on the ellipse. Let's give it coordinates x, y. Now, the equation of an ellipse is x squared over a squared plus y squared over a squared times 1 minus e squared equals 1. That's where a is an arbitrary number and e is the eccentricity of the ellipse. That measures how much the ellipse differs from a circle. It doesn't matter if you replace x by minus x or y by minus y. The new point still lies on the ellipse. So the ellipse is symmetric in the x-axis and also in the y-axis. And this symmetry means that we don't just have a single focus, f, there's also a second focus, f dash. And we don't just have a single directrix, we have a second directrix as well. So let's see the connection between these and your flower bed. Well, this focal distance is just E times the distance of P to this directrix, and this focal distance is just E times the distance of P to this directrix. Adding those two things together, it means that as the sum of the focal distances is just E times this distance. In other words, some fixed number. So the sum of the focal distances is the same for all points P on the ellipse. So you see, John, that's why you can construct an elliptic flower bed by using two pegs at foci of the ellipse and a rope to trace out the ellipse.
Do the other conics have focus directrix properties too?
Yes, indeed. Why don't you go to see the parabola at Martlesham Heath?
On David's advice, I set off for the British Telecom Research Facility. Based at Martlesham Heath in Suffolk, the facility deals with the design and testing of a wide variety of telecommunications equipment. My contact was Dr. Mike Mealer, a leading authority in antennae and satellite design. I began by asking him what that had to do with conic sections.
Well, ever since the early days when people like Cassegrain and Gregorian worked on telescopes and used conic sections as a means of producing focused beams of optical light, the principle of the conic section has been well established as a means of collimating, focusing beams of electromagnetic radiation. And microwave radiation is no exception.
Why are these dishes parabolic?
Parabolic reflectors have the property of taking the radiation from a focal point and producing a parallel beam of rays. So therefore, in effect, they can take the radiation from a primary source, in this case a microwave horn antenna, and produce a collimated or focused beam, which we can then shine at some distant source, like in this case a satellite. Simple parabolic reflector antennas are very useful at microwave frequencies, and they are very commonly used in satellite communications, both at the ground stations and on board the satellite.
Are all satellite dishes used in the same way?
As far as the ground station antennas behind us are concerned, they are seeing parallel beams of microwave radiation which emanate from a satellite striking their main reflectors. So the same property holds in reverse. Effectively, Snell's law will operate at the surface of the reflector and the rays will be redirected to the focal point, which in this case will be the microwave feed horn, which will then act as a receiver rather than a transmitter.
Mike went on to explain that these dishes beside us had a different configuration. Although the primary dish was still parabolic, there was a secondary hyperbolic mirror that is placed at the focal point of the parabola. The benefit of this so-called Cassegrain arrangement is that the main source of illumination comes from behind the antennae, is then reflected by the hyperbola onto the parabolic dish, producing parallel rays for transmission. I asked Mike why that system was used.
Firstly, we can conveniently locate all of the electronics in a nice watertight container behind the antenna, and it isn't sitting out there in all weathers. And it also means that the electronics, which would be quite sizable, is not blocking the rays as they are reflected from the main paraboloid on their way to the satellite.
Dr. Mealer's answers had given me a lot to think about, and so I was glad to see David waiting for me, and particularly pleased with the offer of coffee. David, Mick mentioned Snell's law. What is that?
Well, suppose you have a plane mirror and an incoming light ray, which is reflected from your plane mirror. Then these two angles are equal. That's what Snell's law tells you.
As simple as that?
Well, not quite. It may be that your mirror surface is curved, and then you need the tangent to the curved surface. An incoming ray is reflected from the curved surface, and these two angles are equal. The angle between the tangent and the incoming ray, the tangent and the outgoing ray.
So what if that curved surface is a conic?
Well, let's start with a parabola. There's the focus and the axis. Then incoming light is reflected from the parabola back through the focus. And why is that? Well, if I draw the tangent to the parabola at the point of reflection, then these two angles are necessarily equal. As Snell's law says they must be.
So what about ellipses?
Let's draw an ellipse, and it's two foci. Then a ray from either of the foci that goes towards the ellipse is necessarily reflected back from the ellipse to the other focus. So if I draw in a tangent at the point of reflection, then the angle that the incoming light ray makes with the tangent is equal to the angle between the tangent and the outgoing light ray. In fact, for every conic, the rays from one focus are directed to the other focus. In the case of the parabola, the other focus is effectively at infinity, just like our example of the satellite dish.
So what about the hyperbola?
Well, if these are the two branches of your hyperbola, and these are its foci, then an incoming ray going towards one focus of the hyperbola is reflected off towards the other focus. That's because, again, these two angles are equal, and the antenna that you've just looked at doesn't actually have a second branch of the hyperbola at all. It collects the reflected rays at the second focus, where all the electronic equipment is situated.
By this stage, things had started to make a lot more sense, and I was looking at the world in a completely different way. Conics seemed to be everywhere I turned.
The torch was lit amid the ruins of the ancient birthplace of the Olympic Games, the altar of the Greek god Zeus. The ceremony took place at the Temple of Hera in Olympia, where a Greek actress dressed as a goddess used the sun's rays to light the torch.
The other science is astronomy, radio astronomy, in fact. And here the statistician can help the astronomer to answer the big questions about the origins of the universe.
So in order to collect as much energy as possible, we use giant reflecting telescopes like this one. The painted metal surface is made out of hundreds of panels in the shape of a paraboloid. That means the signals come down from space and are reflected from the surface to the focus high above me.
It was then that David decided to get in touch again. Hello. Hi, David. There was one more example that David wanted me to see, but this time they were much further afield. I'd like to, yes. It was Sir Isaac Newton that pointed out the advantage of locating optical telescopes on mountain peaks above the clouds. The idea was then taken up by Charles Piazzi Smythe, the Astronomer Royal, when in 1856 he set up an observatory at 8,000 feet on Tenerife. Now there are many large telescopes throughout the Canary Isles, including a group belonging to the Royal Greenwich Observatory. Named after the astronomer William Herschel, this particular observatory on La Palma houses an impressive optical telescope. But rather than using lenses, they use mirrors to avoid colour dispersion and other problems. But what did that have to do with conics? To find out, I asked Renee Rutten, the chief support scientist. And you're the head of astronomy here.
That's correct, yeah.
Now, I understand this is one of the largest optical telescopes in the world.
Yeah, that's true. Yeah.
Tell me how it works.
The best way to explain how the telescope works is by explaining the light path of the stars. The light of the star comes in through the dome, strikes the primary mirror, which is a parabolic mirror, and the light that strikes this parabolic mirror is then reflected up to the prime focus, where we can put instruments for the observers to use.
What do you use the prime focus for?
The prime focus is mainly used for wide field imaging and spectroscopy, where observers want to observe a large part of the sky.
So what other ways can you use the telescope?
Apart from the prime focus, we have the Cassegrain focus. When observers want to use only a small part of the sky, they are better off using the Cassegrain focus, and we can mount instruments there as well.
René explained that the Cassegrain focus was a way of combining two conic mirrors, the parabola and the hyperbola, to improve the resolution of the telescope. Like the prime focus, the major component was a large parabolic mirror mounted at the lower end of the telescope. To achieve the smoothness of curvature required, the mirror is coated with a fine layer of aluminium and then encased in protective covers to minimize dust deposits. The petal-shaped covers then open when the telescope is functioning. Above the parabolic mirror and shrouded within a light protective cover is the second mirror, the hyperbola. The instrumentation below the telescope was very large and cumbersome, making it heavy to move. To allow astronomers to follow the elliptical patterns of the stars, not only does the telescope move on its axes, the dome can also rotate through 360 degrees. The operation of the two configurations, the prime focus and the Cassegrain, reminded me of the antennas at British Telecom. Rather like a home satellite dish, the prime focus consisted of a simple parabolic mirror that reflected light to its focal point, where imaging instruments were mounted. The Cassegrain focus consisted of the parabolic mirror with a secondary hyperbolic mirror mounted at the parabola's focal point. This reflected light through a hole in the parabolic mirror towards the focus of the second branch of the hyperbola, just as David had explained. So, conic sections have far more uses than I would ever have envisaged. Yet it doesn't quite end there. It was actually a misshapen parabolic mirror that caused the problem with the Hubble Space Telescope. But it was understanding the reflection properties that enabled scientists to put the Hubble right again.
The Space Shuttle Endeavour returns to Earth after one of the most difficult operations in space flight. Their mission: to locate the Hubble Space Telescope and to repair its defective vision. It was soon after the launch of the Space Telescope that NASA announced there was a problem.
The conclusion we've come to from that is that there's a significant spherical aberration appears to be present in the optics.
The mistake had arisen 10 years earlier when the primary parabolic mirror had been ground to the wrong shape. It was not truly parabolic. The result, had anyone checked it, was that light falling on different parts of the parabola was focused unevenly behind the mirror, causing a sort of short-sightedness. The astronauts aboard the Endeavour needed to correct that defective vision. And to do that, they needed to reach Hubble and install corrective equipment. Spectacles for the telescope. Not lenses, however, but mirrors. As it exists, the light path within the telescope is complex. Incoming light is split into 4 beams using a Cassegrain arrangement, each sent by a series of mirrors to separate experimental equipment. Each of these beams was blurred, misfocused. What was needed was a box of tricks that could replace an existing piece of equipment. A small price to pay in the circumstances. The 4 mirrors, installed remotely, could then intercept the light path and send focused light to each of the different imaging systems. The result was COSTAR, the Corrective Optic Space Telescope Axial Replacement, a package developed by scientists from around the world in association with NASA.
And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Once in space, the astronauts aboard Endeavour had to locate the telescope, match its orbit, and install the equipment. Finally, the job done, Hubble's aperture door reopened for business. Just after Christmas 1993, the COSTAR mirrors in place, the first images were received.
Perfect, perfect, perfect.
Before and after is this one versus this one.
They were as good as anyone could have hoped for. The trouble with Hubble was over.
I have to say, it's been an interesting experience for me. I hope you've enjoyed reflecting on conics, particularly their reflection properties. But just remember, conics are everywhere.
The OU returns to BBC Learning Zone later and takes a look at whether high-tech solutions are really the best way to curb vehicle emissions. Catalysts Against Pollution is at 5:45. After that at 6:10, take a look around the Palazzo Pubblico in Siena. And finally, there's a look at how to make and test a pressure vessel, made without floor, at 6:35. If you'd like to know more about BBC Learning Zone, you can telephone the BBC Education Information Line on 0181 746 1111.